Hello folks, welcome to CodeCrucks. In this video, we will talk about minimization of DFA using equivalence state method. State minimization is required because it may be possible that many DFA represent the same language and the architecture of DFA would be different. For example, if we look at M1 and M2, both accepts empty string. If we read 1A, both will reject it. When we read second A, both will accept. For third A, both will reject. For fourth A, both will accept. So if we continue in this way, then we can realize that language accepted by both the DFAs are same. That is epsilon, AA, 4A, 6A. In short, both DFA accepts language having even number of A. Now, number of states in both DFA are different. But if we can find out the DFA with minimum states, then it would be easier for us to trace as well as that would be faster. There could be some equivalent or redundant states in DFA which will not improve the power of DFA, but rather they will just increase the effort to recognize the string by introducing unnecessary transitions. If we consider this DFA, and let us find out some redundant states into this. If we read A from state 1, we are moving to state 3, and if we read B from state 1, we are moving to state 5. Similarly, if we read A from state 2, it leads us to state 3, and if we read B from state 2, it leads us to state 5. That means this state could be a redundant state. Both are going to same state when we read A and both are going to same state when we read B. So this could be redundant or equivalent state. So if they are equivalent, we should eliminate them from the DFA. So DFA would be a smaller one. Let us check how to identify equivalent states. In DFA-D, two states P and Q are said to be equivalent if it satisfies following condition. That for some string W, if we start from state P and it is going to final state, that implies if we read W from state Q, then also we are going to the final state. Then we can say P and Q are equivalent. Or if we read string W from state P and we are going to non-final state, then on reading W from Q, also we should go to the non-final state. Then we can say that P and Q are equivalent. If length of string W is 0, then we'll call P and Q as a 0 equivalent. If length of string is 1, we will say P and Q are 1 equivalent. If length of string is 2, then P and Q are 2 equivalent, and so on. In general, it could be n equivalent. Let us understand the algorithm for minimizing the states in DFA. So our original DFA could be Q, sigma, delta, Q0 and F. And minimized DFA could have a reduced number of states. So we will represent it as a Q dash, where Q dash would be subset of capital Q in original DFA. Sigma will not change. Transition functions will definitely change because now we have a different set of states. Initial state in both DFA would remain same, but final states can change. So we have a Q dash, delta dash and F dash are modified versions of the original DFA. In step 1, we have to divide the set of all the states, that is capital Q, into two sets, set of all non-final states and set of all the final states. And we will call this partition as a P0. So initially, we can always find P0 without doing much processing. Simply, all non-final states we have to put it into one partition and all final states we have to put it into the another partition. So assume that for some hypothetical DFA, we have capital Q as Q0, Q1, Q2, Q3, Q4 and Q5. So the DFA contains 6 states and the final state of this DFA is Q5. To create the initial partition P0, we will divide it into two halves. Set of all the non-final states, that is Q0 to Q4, and set of all the final states, that is Q5. Next, we have to initialize k is equal to 1, and this is an iterative process, so we will keep iterating through step 3 now. We have to find pk by partitioning pk minus 1. So from p0 we will derive p1. Once we have a p1 we will derive p2 from that and so on. And to derive pk from the previous partition, what we need to do is, in each set of pk minus 1, if two states of any set are distinguishable, we will split the set into different sets in pk. So assume that p0 is the current partition, from that we have to derive p1. So if any states in in q0, q1, q2, q3, q4 are distinguishable, then we will split this group into two subgroups and we will create a new partition called p1, something like this. Assume that q0 and q2 are distinguishable from q1, q3 and q4, but q0, q2 itself are not distinguishable so far, and q1, q3, q4 are also not distinguishable so far. Concept of distinguishable we will learn on next slide, but this is the partition. And we have to keep repeating this step 3 until pk and pk minus 1 are same. So right now they are not same. So again we will go back and we will check whether q0 and q2 are distinguishable or not. If they are, we will split them. If not, we will carry forward them as it is. And same check we will do for the states in q1, q3, q4. If they are distinguishable, then split it. So q1 is distinguishable from q3 and q4, so we are doing this. So we are getting the p2. Again we will go back to step 3 and we will iterate to check whether q0, q2 are distinguishable and q3, q4 are distinguishable or not. And assume that in p3 we are getting the same set. That means q3, q4 are not distinguishable anymore now, and q0, q2 is also not distinguishable anymore. So when this happens, we have to stop. We have to stop because p2 and p3, that is pk and pk minus 1, are identical. Once we reach to this condition, all states of one set are merged into single state. So now q0, q2 we have to treat it as a single state, and q3, q4 also we have to treat as a single state because they are identical, or we can say they are redundant. So we can eliminate one of them. Either we can put them into into one state, or we can rename them. For our simplicity, we are renaming q0, q2 as A and q3, q4 for B. And with this, now we have to construct the DFA. So that would be the DFA with only 4 states. In original DFA, there were 6 steps. So this is the algorithm for minimizing the given DFA. It's not always possible to construct a modified or the compressed version of DFA, but if it is possible, this algorithm ensures that we will get the minimum DFA, that is DFA with the minimum number of states. 2 states P and Q are said to be distinguishable in pk if for any input alphabet A belongs to sigma. We will find out what are the transitions on input alphabets of each states. When we find the transition of P and Q on all the alphabets A, B, C, D, whatever it is given, and if they are in same state or in same group in pk-1 partition, then they are not distinguishable because the transition goes to same set of states. So they are not distinguishable, and this term will be more clear when we will discuss the example. Assume that this is the DFA and we have to find the minimized DFA of this DFA. This is the transition table, but as we can see from the diagram, Q3 is unreachable. So if we start from Q0, there is no way we can go to the Q3. So transitions of Q3 we can always avoid because it is not reachable at all. So this we will consider as for the processing. Let us first derive P0 or the 0 equivalent partition. P0 means what? The set of all the non-final states and set of all the final states. So in given DFA, Q0 is the set of non-final states and Q1 and Q2 are set of final states. So this is the P0, very simple. Now we will try to derive one equivalent. So we will read one character at a time from Q1, Q2. Q0 is the only state in that set, so it's isolated and we don't need to process it. If there are multiple states, they might be identical or they might be equivalent. So we will make a test for Q1 and Q2 to check whether they are same or not, or they are equivalent or not. When we read A and B from Q1 and Q2, during computation of P1, we are remaining into the same set of P0, and that's why Q1 and Q2 are considered as the equivalent or redundant or equivalent state. So P1 is identical to P0, so we have to stop here, and we will either remove Q1 or we can remove Q2, or we can give some different name to this combined or equivalent states. So let us consider A is equal to Q1 Q2. So our DFA will look like this. All transitions which were going from going to Q1 or Q2 will now go to state A. Wherever there was Q1 or Q2 in the transition diagram, transition table, it will be replaced by A. And those two rows of Q1 and Q2 we have to remove. Instead, we have to put only A. As Q1 and Q2 are final state, we have to mark A as a final state. So this is how we have minimized the DFA from 4 states to 2 states only. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.